Our section of this day is about Ostwald dilution law. According to Arrhenius' theory of electrolytic dissociation, electrolytes in aqueous solution generally undergo partial dissociation and finally establish an equilibrium between dissociated molecules and undissociated molecule. Ostwald in 1888 applied this condition and also law of chemical equilibrium to such equilibrium systems to establish a relation between degree of dissociation and electrolytic concentration. That mathematical relation is known as Ostwald dilution law. To explain the concept, consider the dissociation of an electrolyte Ba of concentration C moles per liter and alpha is the degree of dissociation. According to Arrhenius' concept, the electrolyte Ba in aqueous solution dissociate as B plus plus A minus, dissociate into cation and anion. Suppose initial number of mole is 1. Initial number of mole means the electrolyte is not dissociated yet. Then there is no ions and we can write it as 0. And suppose alpha be the degree of dissociation. That means out of the 1 mole, alpha moles are dissociated. So, alpha is far less than 1. Then here we will get alpha B plus and alpha B minus. Why it is so? Coefficient is 1, 1, 1. When 1 mole Ba is dissociated, 1 mole B plus and 1 mole A minus is obtained. So, alpha mole Ba dissociated means alpha moles of B plus and A minus are formed. This is the reacted number of moles. After that, system going to equilibrium. At equilibrium, Ba remain is 1 minus alpha. Here we have alpha and alpha. And also initially we have mentioned that concentration is C. Therefore, in this solution we can write equilibrium concentration as this is equilibrium number of moles. Now we have to write equilibrium concentration as C into 1 minus alpha, C alpha and C alpha. You have studied about law of chemical equilibrium in a chapter called equilibrium in 3rd semester. According to that concept, for this equation 1, equilibrium constant K can be written as concentration of B plus into concentration of A minus divided by concentration of Va, concentration of product by concentration of reactant. Substitute B plus, that is C alpha, again A minus C alpha divided by Ba means C into 1 minus alpha, that is the concentration at equilibrium. Then we will get C square alpha square by C into 1 minus alpha. 1 C is cancelled. Then K equal to C alpha square by 1 minus alpha. Suppose V is the volume of solution. V is the volume of solution having 1 mole of the electrolyte. Then K can be written as, if V is the volume of solution having 1 mole, that means concentration equal to N by V, number of moles by volume. Here number of mole is mentioned as 1 mole. So concentration is 1 by V. Instead of this C, we can write it as alpha square divided by 1 by V into 1 minus alpha. The relation we have obtained in the last slide is K equal to C alpha square by 1 minus alpha, or K equal to alpha square by alpha square by V into 1 minus alpha. These are two relations which we have obtained from the previous discussions. Since we are considering about, if we are considering about weak electrolyte, under such condition alpha is negligibly small compared to 1. So in denominator we can neglect alpha. So K become equal to C alpha square by 1. That means C alpha square, or K equal to alpha square by V. From these two equations, again we can see that alpha equal to root of K by C, or alpha equal to root of K into V. These two equations, which equations? Equation 5 and equation 6 are called Ostwald dilution law. What actually this equation means? Ostwald dilution law is a relation between degree of dissociation alpha and concentration or volume. Degree of dissociation alpha is inversely proportional to square root of concentration, or directly proportional to square root of volume. That is the simplest statement available for Ostwald dilution law. Now we have to see what limitations can be tell about Ostwald dilution law. The main difficulty of Ostwald dilution law is that Ostwald dilution law cannot be applied in strong electrolytes. It can be applied only for weak electrolyte. Actually, the problem was not with Arrhenius. The real problem was the theory about which this Ostwald dilution law has been derived, Which was the theory? The basic theory of Ostwald dilution law was Arrhenius theory. In Arrhenius theory, Arrhenius postulates that all the electrolytes are partially dissociated at normal concentration, and degree of dissociation increases with dilution. But it is true only in the case of weak electrolyte. In the case of strong electrolytes, they are completely dissociated even at moderate concentration. So at that conditions, the Ostwald dilution law will definitely fail in the case of strong electrolytes. Now we have to see what are the applications of Ostwald dilution law. First application, we can calculate degree of dissociation of weak acids and weak bases. Degree of dissociation of weak acids and weak bases. Both are weak electrolytes. So we have to see the examples. Consider weak acid HA. The dissociation of HA to H plus A minus attain an equilibrium at a particular stage of dissociation. Suppose C is the concentration of the solution and alpha is the degree of dissociation. Then initial concentration C, here it is 0, 0 before dissociation. But at equilibrium, this is C into 1 minus alpha, C alpha and C alpha. All these things we have discussed for general electrolyte BA. Now it can be applied in specific case. That is the difference. From this we can say that dissociation constant of acid, so it is K, not Ka. Ka equal to C square alpha square divided by C into 1 minus alpha. For weak electrolyte we can neglect alpha, so Ka equal to C, one C is cancelled, alpha square, and alpha equal to root of Ka by C or alpha equal to root of Ka into V. Since concentration and volume are inversely proportional, we can write as root of Ka into V. Here also we have Kv instead of Kv. Here we have Kav because we are discussing about an acid and dissociation constant of acid is Ka. In the same way, we can see the dissociation of weak base BOH. Dissociate as B plus plus OH minus. Initial concentration is C 0 0 and at equilibrium concentration is C into 1 minus alpha, C alpha and C alpha. When proceed like the case of weak acid, we can see that Kb equal to, instead of Ka we have Kb here because we are dealing about weak base, so dissociation constant can be written as Kb. Then Kb equal to C square alpha square by C into 1 minus alpha by cancellation, and after that we will reach a relation Kb equal to C alpha square and alpha equal to root of Kb by C or alpha equal to root of Kb into V. Okay, so we have obtained 4 relations. This is the calculation of degree of dissociation alpha for weak acid and weak base. Now the second application is, it was the first application, and second application is calculation of pH of an aqueous solution containing weak acid and weak base solution. pH of an aqueous solution containing weak acid or weak base What is pH? This is negative logarithm of H plus. Okay, this equation can be written as 5. Coming to the previous slide, in this derivation we can see that at equilibrium concentration of H plus is C alpha. So instead of H plus, we have to write here as negative logarithm of C alpha. This is the equation for calculating pH of weak acid if the concentration and degree of dissociation are known. This log is base 10 base log. In the case of base, we have OH minus instead of H plus. So in the case of base, it was for acid, now we have to see base. Instead of pH, we have to write POH. POH is negative logarithm of OH minus. What is OH minus? That is also C alpha. Then POH equal to negative logarithm of C alpha. But we have to see pH. pH is 14 minus POH. This way we can calculate pH of base. Here we have directly getting the pH of acid. These are two second application. These are the second application of Ostwald dilution law. And now to third application. Calculation of ionization constant of acid and base, that is Ka or Kb. Ionization constant of acid is Ka, that of base is Kb. If the degree of dissociation alpha and concentration C of a solution is known. Which solution? Electrolytic solution is known. The degree of dissociation. How to calculate degree of dissociation? Applying Kohl-Roche's law, alpha equal to lambda mc by lambda m0, that relation we know. So if you have been provided with a solution of known concentration, then you can calculate alpha using this equation by measuring the lambda m. So using a conductivity cell, at first you have to go for measuring the conductivity of that solution, molar conductivity of that solution, that is lambda m. Lambda m0 for any electrolyte is already known, that is a predetermined factor. By substituting these two values, you will get alpha. Concentration is known. Then Ka equal to, simply we can write it as C alpha square. What is Kb? That is also C alpha square. So you have to find alpha first through the molar conductance measurement, and that value can be substituted in Kohl-Roche's law to get the final solution. These are the three major applications of Ostwald dilution law. Now we can see one problem from this section of Ostwald dilution law. So far we have obtained around 6 equations for calculating either Ka, Kb, concentration, alpha, pH, pOH, etc. Now the question is, determine the alpha and pH of 0.05 molar NH3 solution. You have been provided with Kb, which is 1.77 into 10 raised to minus 5. What are the parameters to be determined? They are alpha and pH. At first, what is alpha? Ammonia is a known base, which is a weak base. So alpha can be calculated through root of Kb by C. What is Kb? 1.77 into 10 raised to minus 5 divided by concentration is 0.05, and we will get the solution 0.0354. It is alpha. Then pH. For a weak base, it is difficult to find out pH directly, so we have an equation 14 minus pOH. So the next question, what is pOH or how to calculate it? That is negative logarithm of concentration of OH minus. For that we had the equation C alpha. Okay, then you have to see C alpha, negative logarithm of concentration is 0.05 into alpha is 0.0354. Then you will get negative logarithm of 0.00177, which is equal to 2.5752. This is the equation for this is the value of pOH, but actually you have been asked to find the value of pH. Then we have to substitute pOH here. 14 minus 2.752, that is 11.248. This is the pH. So we have obtained alpha as well as pH. Okay, thank you.